Okay, so good afternoon. Today, hopefully, I'm going to finish these slides on multi-threaded kernels. So that should be the goal. We'll see if we can achieve that goal. Now, so I got during the reps meeting today, I got 2 comments about the lectures. So mostly people, majority of the students who participated found the lectures to be effective or very effective. But there were some who felt like it was not effective and there was room for improvement. So that's always the case. So I would love to hear more from those people. So if you're among those who think that there are things that could be improved, please use the form. So if you are, if you remember, there was this oh, excuse me. So these just for a reference, did it download? Yeah. So there was, if you remember, I had these anonymous feedback form. So use this link from the introduction to let me know more specifically what aspect of the lectures you want me to improve. And if you are among those who actually like the lectures the way they are, please go ahead and also voice your opinion. Interestingly enough, in the form that your representatives gave us, there were 2 conflicting points about the lectures. So if I only hear from those who are not happy and I change something, those of you who are happy with the way things are not going to be heard because you're not voicing your opinion. So everybody who is listening to what I'm saying right now, please use this feedback form to let me know what are the things that you like, in particular about the lectures, about the quizzes, and what are the things that you don't like and you think there is room for improvement. And if I get a good pool of feedback, then I can modify things that that could improve your experience in this course. So that's one thing. One of the, in particular, some people, like there was one comment about the length of the lectures that is like 1 hour and 20 minutes is too much compared to the 50 minutes lectures. So I mean, if we go back to in person, that's going to be the case. So I think it's probably because you haven't taken 1 hour and 20 minutes lectures before. Maybe I have no idea, but that's pretty much the norm in the lectures. So yeah, the time is not up to me. So they gave us this 1 hour and 20 minutes lecture slots, and that's what we're using. Okay, so that's pretty much what I wanted to say about the feedbacks that I got. Okay, so going back to the lectures. So again, hopefully I get a chance to finish this set of lectures or slides today. So we started talking about how we can implement synchronization objects. We started with mutexes. The first way to implement them is to disable interrupts and then enable interrupts. Now, what are the problems with this implementation? This simple implementation has some serious problems. The first problem that this has is that we cannot allow users to use these mutexes. So these mutexes that we have implemented with enabling and disabling interrupts only work if kernel threads use them. If a user thread wants to use them, there will be an exception raised, because in user mode, you cannot enable or disable interrupts. So that's first thing. Now, let's assume that you can, let's assume that we allow users to do this. Then the problem becomes that, your users are going to have so much power. If they are able to enable or disable interrupts, they can do mutex.lock and then while empty or while true, and that's it. So your system is done because the interrupts are disabled, and the code inside the interrupt, the code that is running is not going to call any function or cause any exceptions, and basically your system will get stuck there. So that's the first downfall of this implementation. User threads cannot use them. What else? The second problem with this is, even for kernel threads, if you have a multiprocessor system, when you disable interrupts, the interrupts are going to be disabled only on one processor. So if you disable interrupts in one processor, then you have mutual exclusion on that processor. But a thread that is running on another processor is not necessarily mutually excluded to run that piece of code. So because we are just interrupting one, we are disabling interrupts on one processor, the other code that is running on the other processor is not necessarily mutually excluded to enter the critical section. Now, finally, if you're implementing a real-time operating system or an embedded operating system, and let's say all your threads are kernel threads, and let's say you have a uniprocessor system, so everything is fine. So you're not going to deal with the first two issues. The third issue comes and bites you. And the third issue is, as I mentioned, if you remember back in a few lectures ago, I said, when you disable interrupts, you're really not disabling them. You're ignoring them. And the interrupts are going to be buffered somewhere. Now, there are certain interrupts that you really don't want to ignore. For example, if you're writing this for a reactor, a nuclear reactor, and one of the threads calls this mutex lock, and then enters its critical section, and let's say in this critical section, this thread is going to do a bunch of stuff, and it takes time, and some emergency happens. Now your system cannot respond because the interrupts are disabled. So this is extremely bad. If latency and responsiveness is a goal, then you definitely don't want to disable interrupts for a long period of time. So you want to maybe disable interrupts for a few nanoseconds or a few microseconds, and that's it. You have to enable them back because there are certain things that you cannot really ignore, or you should not really ignore. So let's so somebody's asking, so mutex lock, while true, is not allowed in any processor. I really didn't say that. I said if the way you're implementing your mutex is by disabling interrupts, then if you do mutex lock and then while true, you get stuck, right? Because the interrupts are disabled and there is no way to preempt the running thread. So the running thread will run forever until you go and physically turn off your computer. So for that particular implementation, doing mutex lock and then while true is going to be really bad. Now, in other implementations, so let's say we're implementing mutex not with disable interrupt, doing mutex lock and then while true is a bad thing to do, right? As a programmer, why would you do that? Why would you put while true in your critical section? So critical section has a definition. In critical section, you're touching some data, some shared data. So putting it while true inside your critical section doesn't make sense in the programming from the programming point of view. So the issue I raised with mutex.lock and then while true was for the particular implementation of mutexes with disabling interrupts. That would be detrimental to your system. So from the operating system's point of view, it's not a good idea to implement mutexes with disabling interrupts. Okay, so how can we improve this? So the idea is, let's create this class mutex. I mean, we had this class mutex before, but it only had two functions, lock and unlock. And inside lock, we had disable interrupts and then enable interrupts. So actually, for me to go, so the idea is, let's add a variable to our mutex to indicate if the mutex is locked or unlocked, right? And then then we can use disabling interrupts and enabling interrupts to change this variable. Now we'll see how this is going to be beneficial, but that's the idea. So let's add a variable to our class, and then we can use this enable disable interrupts to change that variable. So here is how we're going to do it. Class mutex. Now it has a private element. It's called value, and let's say it's initialized to free. So initially your mutex is free. And then we add a queue to this mutex. So this is going to be the queue of waiting threads. So if one thread has locked the mutex and another thread comes and calls lock, we want to suspend the second thread, but then we want to keep track of them. We want to keep track of all the threads that are suspended in this lock. Where do we put them? We put them in this queue. So these are the two private elements of this class. And then, like before, we have these two public operations defined on mutex, the lock and unlock. Okay, now, before we continue, I want to make something clear. Now, there are two things that we're going to do. So here is the programmer. So your programmer has a code, and the programmer is going to use the mutex. Your programmer is going to say mutex, let's say M, and then at some point, m.lock, and then here comes the critical section. And then m.unlock. And blah, blah, blah. Okay, so this is a critical section for your programmer's code. For example, in the ATM example that we saw, this could be, accessing people's accounts and adding balance, modifying their balance, and so on and so forth. So this is the critical section. So there are variables, there are data that are shared between different threads, and this is critical section. Now, this critical section is programmer's code critical section. Right? This is a critical section of the programmer. So this is what the programmer who is using this mutex cares and defines as a critical section. Now, let's look at mutex. This mutex that we have here has some bunch of variables here. Now, bunch of threads are going to call mutex.lock. So now these variables are going to be accessed by a bunch of threads. And these variables are different from, like, for example, in the ATM example, you might have, accounts, balances, and so on and so forth. Those are your shared variables. But when you start using this mutex, everybody who is calling mutex.lock is going to touch or read this value and potentially get added to this queue. So then these variables become shared variables that are going to be accessed by multiple threads. And the programmer has no idea about these, right? We're hiding this from the programmer's point of view, but at the same time, threads are going to be executed simultaneously and access the internal state of your mutex. So therefore, the internal state of your mutex becomes shared data between threads. And if you want to modify it, you have to make sure that you have mutual exclusion. So this becomes shared data and requires synchronization. It kind of is a loop, right? Because we are implementing mutex to provide mutual exclusion, but then now inside our mutex, we have a bunch of variables and we want mutual exclusion for them. So that's basically where we're going to use enabling and disabling interrupts. So we will use enabling and disabling interrupts to create mutual exclusion whenever we want to touch the internal state of our mutex. So disabling and enabling interrupts will be used for mutual exclusion for the shared variables of the mutex. Then mutex will be used to ensure critical section and mutual exclusion for the user program. Now, here is how we're going to do it. So for lock, to implement lock, we're going to touch those shared variables. Like we're going to touch the value and we're going to touch the queue. So because we want to do that, we're going to disable interrupts. Now check if the value is busy. If the value is busy, it means that the mutex is already locked. So we're going to add this thread, this TCB, to the list of waiting threads. And we're going to change the state of this thread to waiting. And then we're going to choose another TCB, another thread to run. So this is where we're going to ask the scheduler who else can run now, because this thread is not going to run anymore. And then we're going to just call the thread switch that we saw previously. We're going to switch from this thread, and this thread is going to go to sleep. Now, after this line, another thread will start running, not this thread. And some time later on, this thread will wake up, hopefully with the lock. So somebody else who has the lock. So here we checked and the lock was busy, so somebody else has it. So at some point, when this guy who has it releases the lock, let's say it gives it to this guy, to this one that is now going to sleep. So when you wake up, you have the lock. So you wake up from after this function. Now we can assume that when you wake up, you now have the lock. So all we need to do is to change your state from waiting that we made to running. Now you're running and you have the lock. And if the value, and then you return. And if the value was not busy, it means that the lock was free. Then all you need to do is to make the value busy and get out. Before getting out, you enable interrupts and we terminate out. So again, now this section is kernel critical section. Because kernel is, implementing locks, And this is the critical section for kernel, because as I said, this value and this queue, this ready list, these two are shared values and we want them to be protected. So this is our critical section. For our critical section, we're using disabling and enabling interrupts. And once we have this implementation, now users can borrow this lock. Not users, like programmers, can borrow this lock and implement their code and provide critical section and mutual exclusion for their code. As we will see, this still cannot be used by the programmer because we are still using this enable disable interrupts. So, but it at least can be used by kernel code, and it doesn't have some of the downsides of the previous implementation. We'll talk about that in the coming slides. Now let's look at unlock. How does unlock work? Again, to provide mutual exclusion, we disable interrupts at the beginning. Now we check the wait. Here we want to unlock, right? We want to release the mutex, unlock it. We look at the waiting list to see if anybody is waiting. If somebody is waiting, we're going to wake them up. How do we wake them up? We're going to just change their state. We're first of all, we're going to remove them from the list and make their state ready. We're not going to start running them, right? All we're doing is we're going to pick them from the waiting list and put them on the ready list. If you remember the life cycle of threads, it was init, it was ready, it was waiting, and it was running and finished. So your thread that is blocked on the lock is here, and some other thread is running here, So then the running thread picks this TCB and puts it on ready list. Says, okay, now you don't need to wait anymore. I'm releasing the lock. And when you wake up, you're going to have the lock. So we add you to the ready list, and note here that in this case, this thread does not change the value to free. It keeps the value busy. So the thread that is unlocking is supposed to make the value free, but because it saw that there was another thread waiting, it just made that thread ready and did not change the value. If there is nobody waiting, then change the value to free and exit. Now what happens? So after this thread exits, and let's say it gets suspended or it finishes, this thread that was put on ready list probably gets it scheduled at some time. Where does it wake up? It wakes up from here. Now it can assume that now I have the lock because I woke up, right? Because that's the only reason I'm awake now. Somebody released the lock and gave it to me. So I have the lock and now I start running. So it makes it running and it enables interrupts and gets out. As before, we are disabling interrupts and going to sleep. And when we wake up, we enable interrupts, right? So there has to be some convention on who gets to disable interrupts and who gets to enable interrupts. So the underlying idea here is that we're using enabling interrupts and disabling interrupts to create mutual exclusion for the mutex internal state, which is basically the two variables, the value and the waiting queue, the queue of waiting threads. I got two questions. So that's kind of strange. You have different instances of mutex, though. I'm not following. So we're actually talking about different ways of implementing mutex. We started with talking about mutex in without any internal state and just using it, enabling and disabling interrupts. And then we talked about why that's a bad implementation. Then we added some internal variables or internal fields or internal elements to our Mutex class. And this is the second implementation. So I was not following the question. If you can clarify, that would be great. So where is the value changed from busy to free? Here is value changed from busy to free. So the one who asked the previous question says you are saying the value is a shared car. Yes. So this value is in the mutex. So it's whoever is working with the mutex, calling lock or unlock, might actually use this. So in order for us to now make sure that only one thread accesses this value, we're using disable interrupts and enable interrupts. So because we have this disable interrupt and enable interrupt, we have mutual exclusion. So whoever can disable interrupts, the other ones cannot get into read the value or change the value of this variable or manipulate the waiting list. Okay, all makes sense now. Okay, good. Okay, now let's discuss this solution. So this was our take two. Let's see what did we improve on the previous implementation and what are the existing downsides still. So first of all, we talked about this. Why are we disabling interrupts at all? So we're doing that to make sure that we have mutual exclusion when we are touching the internal variables of the mutex, right? So as I mentioned before, now between disable interrupts and enable interrupts, we have this critical section. This is the critical section of the mutex, which is different from the critical section of the programmer. In the ATM, for example, in the ATM example, your critical section is for the balance and the accounts and all of that. But here, this critical section is on the internal variables of the class mutex. Now, what are the good things about this implementation? So one thing that we improved compared to before is we are disabling interrupts and enabling them for a really short amount of time. Let's say the ATM example. So our programmer has m.lock and then like a lot of code here. So it takes like, 2 minutes to run this code and then m.unlock. Right? So let's say this critical section for programmer, this is where you read from the, your database, you bring the account, you check the balance, you add the balance, you save it, and so on and so forth. And let's say this takes 2 minutes, and this is your critical section. Now, in the first implementation where we disabled interrupts in the lock and enabled interrupts in unlock, we are disabling interrupts for 2 minutes. For 2 minutes, our system is not going to get interrupted, and that's bad. With this second implementation, we only disable interrupts inside this lock to change the value not to busy, right? Inside this lock, we disable interrupts. We change the value from free to busy, and that's it. And then we enable interrupts. So in the second implementation, the amount of time that we're going to disable interrupts is for few instructions. For only few instructions, we disable interrupts, we change the internal value, internal state of the mutex, and then immediately we enable interrupts. And then when we are inside the critical section in these 2 minutes, interrupts are enabled, right? So this time we have shortened it dramatically, right? From like 2 minutes to just few cycles to execute those few instructions inside the mutex.lock. So hopefully this makes sense now, right? So we fixed one problem with the previous one, which was long time of disabling interrupts. Now we have shortened it dramatically, and it's independent of how long the critical section of the programmers are. We don't care, right? It's just these instructions that have to be executed. And during these instructions, we are disabling interrupts, and then we enable interrupts again. And this is regardless of what the programmer is going to do with the mutex. Whereas in the first implementation, if our programmer has a really long critical section, during that critical section, the interrupts are going to be disabled, and that's bad. Okay, but let's also talk about one detail here about who disables interrupts and who enables interrupts. So we're disabling interrupts at the beginning of lock, and there is a chance here that we context switch, right? So where should we enable interrupts? I've kind of answered that question when I was talking about this. So you don't want to enable interrupts here. If you enable interrupts here, then you will be touching this ready list without having mutual exclusion, and that's bad. So there's a shared data, this ready list. If you enable interrupts there, you don't have mutual exclusion on your shared data, and that's bad. So you will have trouble. So can I do it after this ready list? After I touched the ready list, now I don't have any other, let's say, shared variable to touch. Can I enable interrupts here? And the answer is still not. Still, it's not a good idea to enable interrupts after this list. The reason is if you enable interrupts before you context switch to the new TCB, another thread could come right before you context switch. You could get interrupted, and another thread could come up and could then let's see. Yes, so another thread could come. So maybe you enable interrupts here. Let me see, after putting thread on wait list. Right, so I put this thread on the wait list, but before I context switch or switch to the new thread, I enable interrupts. Now, it could well be that the thread that has locked the interrupt disables unlocks the mutex, and then sees that you are in the ready list, right? You have put yourself in the ready list. So let's say thread 1 comes, checks the value, and the value is, let's say, busy. So we put T1 on wait list. But before we context switch to another thread, let's say the thread that has locked the mutex unlocks the mutex, right? If that happens, then that thread will run the unlock code, this code, and looks at this waiting list and sees that T1 is in this waiting list, right? So it puts T1 on the ready list, right? So basically it undoes what we just did here. So here we put ourselves on the waiting list. Now somebody comes and puts us on ready list, and next time we wake up, we're going to wake up from this here. So again, we're going to context switch and think that we should be waiting. Whereas no, you should actually start running here. So when you wake up, instead of running this code, you're going to be running this code, so which is a context switch. So instead of continuing, you're going to context switch to someone else, which is bad. So anyhow, you cannot enable interrupts anywhere here. So if you can't enable interrupts anywhere here, what can you do? The answer is we're going to have this convention that whoever wakes up is going to turn the interrupts on, enable the interrupts. So when you go to sleep, you turn them off, and then when you wake up, you turn them on. So it's going to work like this. So you disable the interrupts, you call thread switch. This thread switch context switches to someone else, and that someone else, when they wake up, they enable interrupts. Then they do some stuff, and then they disable interrupts and call thread switch. Then you wake up, and then you enable interrupts, and the cycle continues. Okay, somebody's asking, getting really lost here. Could you go over that again? Yes, so let me go over this again one more time. So let me get rid of all the things that I have here. Okay, let's talk about why we cannot enable interrupts here. I think this one is easy, because if we enable interrupts, then another thread can come, and we're in the middle of, manipulating the state of the lock, and we want mutual exclusion, so it's against mutual exclusion. So that's bad. Now, why can't we enable interrupts after we're done with manipulating the shared states? So the shared state here is this the shared state is basically this guy, right? Waiting.add, right? I cannot enable interrupt before I manipulate waiting. Now the question is, can I enable interrupts after that, but before I call thread switch? And the answer is that no, you shouldn't, because if you do so, if you enable interrupts, it could be that the timer, let's say, goes off, right? So let's say here, after I do this, I do enable interrupts. And right after I enable interrupts, before I run this second line, this thread underscore switch, timer interrupts goes off. Timer interrupt goes off. We go to the interrupt handler. Now kernel is running. Kernel decides to context switch to some other thread. Now let's say that kernel context switches to the thread that has locked the mutex. Now this thread runs, and let's say it finishes, and it calls unlock. Now this unlock, what does it do? It goes and checks this waiting list, right? This waiting queue. In the waiting queue, you're there because you put yourself there, right? So you put yourself in that waiting list. Now, the thread that calls unlock finds you there and says, oh, okay, so somebody's waiting, I'm going to wake them up. It changes your state. It removes you from this list. Now you're no longer in the waiting. and puts you in the ready list. Now, and let's say it finishes, gets out. And at that point, again, let's say we go to the kernel and kernel finds you, now you're on the ready list. So maybe kernel now schedules you. Now, when you start running, where are you going to run again? So you're going to run again after this line that you enabled interrupts. What is that line? It's this thread switch. What does this do? It context switches to someone else. So what happened? You were supposed to now run because somebody unlocked the mutex and gave it to you. But what did you do? You context switch to someone else again. That's why it's a bad idea to enable interrupts before you call thread switch. You want to wake up on this line. You want to wake up on changing your state to running and enabling interrupts and getting out. But if you enable interrupts before thread switch, you can screw things up. Hopefully I answered the question. How do I get? Okay, we talked about this as well. Now, what are the problems with this implementation? This take two. Take two solve the issue with disabling interrupts for a long period of time, but it still has problems. The first problem is we still cannot allow user threads to use the mutex, right? Because user threads are going to not be able to enable or disable interrupts. So we still haven't solved this problem. It still doesn't work on multiprocessors because, again, disabling interrupts that we're now using to manipulate the state of the mutex are only valid if you have a single processor system. If you have multiprocessor system, disabling interrupts for mutual exclusion is not going to work. So these two problems we still haven't answered or resolved. So to resolve this, we will have to get some help from the hardware. So far we assume that the only atomic operations that we have is the load and store. Now we'll need more atomic instructions. And in particular, we're interested in atomic read, modify, write instructions. So I'm pretty sure you have seen these in ECE 252. But these instructions, so a load goes to an address, reads that address, and brings the data back for you. And a store goes to that address, writes something there, and that's it. And as we said, we're assuming that this operation is atomic. Now, with read, modify, write instructions, we're going to atomically read an address, possibly modify it, and write to it at the same time, atomically. So all three, reading it, modifying it, and writing the result back, are going to happen atomically. And then we use these instructions to implement mutex. So let's look at some of these instructions. Oh, I got another question. Okay, so the solution is to have another thread turn on interrupts. Yes, so the solution is you disable the interrupts and somebody else comes and enables it. And then they disable interrupt and context switch to you, then you enable interrupts, and so on and so forth. So it's kind of like we switch roles. Somebody disables, somebody enables, somebody disables, somebody enables. Yeah, that's the solution. Okay, so let's look at some of these examples, read, modify, write instructions. So the first one is test and set. So here, please don't mistake this as a function. This is not a function. I'm not defining a function. I'm just telling you what this instruction does. This is the functionality of test and set. So given an address, we read it This is the read. We modify it, and we return that. So, and all of this happens atomically. So all three instructions happen without getting interrupted. And the hardware is going to implement this for us. The same way that the hardware is implementing load and store, the hardware is going to implement test and set. So we don't care. So all we need is for the hardware to tell us that I'm not going to be interrupted in the middle of this. So all three are going to happen or none of them are going to happen, right? I'm not going to be interrupted in the middle. So all three happens and then I can get interrupted, or none of them happens and I can get interrupted. There is the swap. So the swap, you give it an address and a register, and what it does, it reads that address and writes to that address whatever you have in the register, and then changes the register with that original value in that address. So basically swaps the value in the register with the value in that address. It swaps them. And again, this is going to happen atomically. Hardware is going to implement this. So we're going to get a guarantee from the hardware. Hardware signs this, swears to us that you're not going to be interrupted in the middle of this. So all three of them happen or none of them happens. And there is the third one. These are examples. There are more of them, I think. So the third one is compare and swap. So this one, you have an address and two registers. And what you want to do is you want to compare the value in that address with one of the registers, let's say register 1. You compare these two values. If they're the same, then you swap the second register with this address. And otherwise, you return failure. And again, all of this is going to happen atomically by hardware. So these are examples of read, modify, write instructions that are atomic. Now, next, we're going to use these instructions to implement Mutex. And good thing about this is that these instructions are not, only executable by kernel. A user program can also use these instructions. So these instructions are not like disabling or enabling interrupts, because disabling and enabling interrupts is you need to have to run it in kernel mode. These instructions, you can run them in user mode as well. So these are safe instructions for users. Now we want to use them to implement Mutex. So I got a question. What's the purpose of compare and swap? The purpose is to compare and swap atomically. Now, in the past, in some of the exams, I will now show you how to implement Mutex, for example, with test and set. Then I can ask you in an exam, implement Mutex with compare and swap. So that's pretty much the purpose of it being here. Okay, so now let's use test and set to implement a very specific lock that we're going to call SpinLock. Now, once we implement a SpinLock, we will use a SpinLock to implement Mutex. So I'm going to do a level of indirection. I'm going to use these instructions to implement a SpinLock. And why is it a SpinLock? Because we're going to spin. If it is locked, we're going to just busy wait. And then we're going to use this guy to implement Mutex. Okay, so that's the journey we're going to go. Let's look at it. A simple implementation of a SpinLock is this. So first of all, this SpinLock, like Mutex, has only has a value that we initially going to make it 0, and has two operations, lock and unlock. And here is one simple implementation. So how does this implementation work? With lock, I'm going to just while on this test and set, on the value. So what happens? So we know that test and set is going to be atomic. So if this value is 0, this test and set returns 1, and then while returns, because we set it to 1, and excuse me. Yeah, if the value is 0, then we atomically set it to 1. Wait, let me go back, sorry. Test and set returns the result. Yeah, so which is 1, right? Okay, so I was right. So if the value, let me see. No, sorry, test and set returns what was in this address, right? So whatever was in the address, it returns that one. Okay, so let's do it again. So let's say initially the value is, let's say value is 1, or let's say 0. Let's say value is 0, and we call lock. What happens? So if the value is 0, what does test and set do? Test and set sets the value to 1 and returns 0. So the value after this test and set, value becomes 1, and this test and set returns 0. Whatever initially was in the value will be returned. Now you have while 0, so there's no need to wait, so you get out of it. So if the value was 0 and you called lock, after this, the value becomes 1 and you get out of the lock. Now, what happens if others then go and call lock? So if the value is 1 and you call lock, what happens? So what will happen is this test and set sets the value to 1 and returns whatever was in the value. So what was in the value? It was 1, so it returns 1. Now this while is getting a 1, so it will wait. So it will execute test and set again. So again, it calls it on 1, it returns 1. 1, 1, 1, 1. So you're going to wait here. You're going to spin lock. So as long as the value is 0, your lock is going to get out and make the value 1. If the value was 1, then the lock is going to spin. And the value remains 1. So that's how we're implementing mutual exclusion. So with this lock, the first one who executes it, the value is turned to 1, and that first thread gets out. The remaining threads, when they call lock, they're going to spin lock there as long as value is 0, as long as value is 1, until the one who first locked it calls unlock. When you call unlock, the value becomes 0. Now, one of those other threads that called lock, one of them is going to see this 0, and it's going to get out of lock. So that's how you are implementing mutual exclusion. Okay, so this is a spin lock. It's going to give you mutual exclusion. So should we now use this as spin lock and give it to our users to use it for their mutual exclusion? And the answer is, yeah, so this is the implementation. The answer is no. It's a bad idea to give this a spin lock to users as a mutex to use. The reason is the same problem we had with disabling interrupts for a long period of time, the same thing could happen, right? So if you have, let's say if you have 2 threads, And then one of them does this SpinLock .lock, and then 2 minutes of critical section, and then SpinLock .unlock. So for 2 minutes, you have your critical section. Now let's say that you have a multiprocessor, right? The other thread so let's say you called lock and you turn the value to 1, and now you're in your critical section, which is going to take 2 minutes. Now another thread on another processor calls lock. What's going to happen to them? They're going to just a spin lock here. They're going to just spin inside their lock. They're going to just keep calling this test and set, test and set, test and set. For all these 2 minutes that you're in the critical section, that other thread is going to just spin lock for 2 minutes. And this is going to be wasteful for CPU cycles, because we're going to waste CPU cycles on that other CPU, which is bad, right? So the problem with this is that we don't want to give this spin lock to our programmers to use as mutex, because for waiting, instead of waiting, they're going to just busy wait. And we don't like busy waiting. We sort of want them to change their state to waiting, and so that we can context switch and do some useful work instead of executing this while test and set. So yeah, that's the problem, right? So let's first talk about the upsides. What are the good things about this? First of all, we're not disabling interrupts, so we can receive interrupts, so it's good. Second of all, we can give it to our users because we're not using the instructions that are not allowed in user mode. As I said, test and set is allowed in user mode, so we can give it to them. So 2 good things so far. The third good thing is that it actually works on multiprocessors, because test and set, it's a value in the memory, and you can actually execute it from 2 separate processors, and they still the hardware is supposed to do this atomically, so it works. So all good things about this. The problem is that busy waiting, right? So we're almost there. We solved 3 problems, and there is only 1 left, and that is busy waiting. So what can we do? So first of all, before I move on this busy waiting, I will talk about this priority inversion when we talk about real-time systems and synchronization. So wait for this exact definition of priority inversion for that lecture. But just to let you know, the problem happens if you have this busy waiting, right? If there is a thread with higher priority than other threads, yeah. The problem with this, for me to explain this, is that I have to explain so many other things. So let's actually stick to what I initially said. I will come back to this priority inversion when we talk about priorities, and I have a bunch of slides on priority inversion. So just a heads up, this is going to come back. You're not going to be quizzed on this one until we actually talk about it when we talk about real-time systems. So just a pointer now for it to come back later on. So I'm going to move on this one, because if I go into explaining this, I'm going to spend so much time, and I won't be able to finish these lectures. Plus, I have slides for it later on. So just a pointer. Now, this busy waiting is bad, and we want to avoid it. So how can we now do the same thing that we did with interrupts? We were able to shorten the amount of time that we were disabling interrupts. we're going to do the same thing. So we're going to now use a SpinLocks to implement Mutex. How? So we're going to have our class Mutex. Now, inside our class Mutex, we're going to have the value, like before, the waiting list, like before, but we're going to add a SpinLock as well. So these two existed before. I'm adding a SpinLock to my class Mutex, and I still have the lock and unlock. So the idea is I'm going to use this SpinLock instead of disabling interrupts. I will use this SpinLock to modify the shared state. So now I can use this to modify the shared state of the Mutex without me needing to use disabling interrupts to change the state. So in addition to this class Mutex, I'm also going to show you a little bit of class scheduler, because we're going to use the class scheduler, because you know, in enabling and disabling interrupts, we were able to enable interrupts in one thread, and then the other thread would disable interrupts in one thread, and then the other one would enable interrupts. Now with the SpinLocks, we don't want to pass it around. So what's going to happen is the scheduler is going to unlock the SpinLock for us when it finishes context switching to another thread, right? That's why I'm showing you a little bit of the scheduler class as well, because we're going to give the scheduler the task of unlocking the SpinLock, as we will see. So this scheduler itself has a SpinLock because it has this ready list, right? Let's say you have a multiprocessor and you keep deciding who runs next on your different processors. So this ready list is going to be a shared data. For this shared data, you probably want a scheduler, a SpinLock as well. And then in particular, we're interested in this suspend function and make ready function. Let's see how they show up. So let's implement the Mutex first. Let's look at lock. So at the beginning of the lock, I'm going to use my SpinLock. So I'm going to say the Mutex SpinLock.lock. So I use the SpinLock to create mutual exclusion. Then I do like before, check the value if it is busy. Then I put my thread in the waiting queue of this Mutex, and then I call the scheduler to suspend me. Now note here that I'm passing this Mutex SpinLock to the scheduler because I want the scheduler to unlock it for me, right? Because I have locked it here, I want the scheduler to unlock it for me. Otherwise, nobody else can modify the state of the lock, and that would be bad because I'm locking the Mutex and going to sleep, and nobody else can even check the Mutex anymore, which is bad. So this is that. Now, when we wake up, we don't need to do anything. We can assume that we have the lock, and we exit. So we will wake up from here. So we can just exit. If the Mutex is not busy, if the Mutex is free, then I make it busy and I unlock it because I don't need to get suspended. Then I can just unlock the SpinLock myself and get out. Now let's look at unlock. How does unlock work? Again, we're going to lock the Mutex at the beginning. We're going to check to see if anybody is waiting. And if they're waiting, I call the scheduler make ready to make this thread ready. So by that, I'm just going to put this thread change the state from waiting to ready. And if there is nobody waiting, then I just turn the value to free, and at the end I free the mutex. Sorry, I unlock the SpinLock. Now let's ask a question. It's an important question. Can interrupt handler use this lock? Let's say your interrupt handler needs to, access some shared data. Can it use this lock? And the answer is no. Your interrupt handler cannot use this lock. The reason is your interrupt handler is not a thread, so you cannot change the state of interrupt handler from ready to waiting, right? So here, if you look at the scheduler, so let's say you want to lock something, and let's say that is locked already, then you're going to be suspended. An interrupt handler cannot be suspended. So if an interrupt happens, you have to get it done. You have to handle that interrupt. So interrupt handler is not a thread, and it cannot be suspended. Therefore, it cannot use this lock, because this lock will suspend the thread. So only threads can use this mutex. And interrupt handlers cannot use this mutex. So we will have to have a way for interrupt handlers to implement synchronization. So we'll talk actually about this. So if you need synchronization in your interrupt handler, you have to use other things. You cannot use this mutex, because this mutex needs to suspend something, and you don't really want to suspend an interrupt handler. So interrupt handlers are not threads. They cannot be suspended. Therefore, they cannot use this mutex. On top of that, you might create some notion of deadlock. If your thread locks it and then gets interrupted, and then interrupt handler wants to unlock, wants to lock again, and the mutex is already locked, now you have a deadlock, because your thread has locked it and suspended, and the interrupt handler needs the lock, and we cannot go back to the thread because we're in the interrupt handler. So now the system gets into a deadlock. So for these two reasons, we cannot actually use mutex inside our interrupt handler. So how can we actually protect shared data? We can use this as SpinLock, right? The SpinLock was good because it doesn't suspend a thread. It just busy waits, and that's fine. We can busy wait inside our interrupt handler, although that could potentially cause deadlock if you have a single CPU. Let's say your thread uses the SpinLock to lock something, and then it gets interrupted, and then interrupt handler calls lock and starts SpinLocking. It starts, spinning. You have a deadlock, right? So to avoid this, what you can do is you can disable interrupts and enable interrupts when you use the SpinLock. So if a thread is using a SpinLock that is used by interrupt handler, that thread is responsible to disable interrupts when it locks that SpinLock, because if it doesn't disable interrupts and gets interrupted, then you might have a deadlock, right? So I repeat myself again. If you have a thread that uses as a SpinLock, that you know that this SpinLock is going to be used by your interrupt handler, then it's on this thread to disable interrupts before it locks the SpinLock. Otherwise, you could have deadlock. These are actually important. So for your quizzes, make sure that you actually understand all of this. Okay, so now let's look at this suspend. I think the most important thing, let me just complete it. I'm going to just leave the reading of this to you, but I will mention two things. First of all, look at me enabling and disabling interrupts. The reason I'm doing it is because I'm using this a scheduler SpinLock. And this scheduler SpinLock is probably going to be used by interrupt handler. Let's say the timer interrupt handler is going to call the scheduler to schedule another task. So indirectly, the interrupt handler is going to need this SpinLock. So therefore, it's on this thread to disable interrupts before it locks the scheduler SpinLock. So this scheduler SpinLock is an example of what we talked in the previous lecture. That's why I'm disabling interrupts before I lock it. The second thing that I want to mention is this line, that this SpinLock that was passed to us, we unlock it here before we context switch. So instead of making the other thread to unlock or lock this SpinLock, we give that task to the scheduler. The rest of it should be fine. So yeah, I also talked about this, why we're disabling the interrupts, because we want to avoid deadlocks that could be caused by an interrupt handler, like something like timer interrupt handler waking up. Okay. Yeah. So the other thing is, yeah, so this the last bullet talks about why this should happen here and not before the suspend. So it's necessary to call this SpinLock unlock inside this suspend function. You cannot call it before the suspend function, because if you do so, the same bad thing that I just explained with the interrupt getting enabled before context switching, the same thing could happen. So if you do a SpinLock the unlock before calling suspend, the same exact scenario that I explained with interrupts getting enabled before thread switch could happen. Okay. So let's put these two implementations together. So this one is the implementation with disabling interrupts, and this one is the implementation with the SpinLocks. And as you can see, they're very similar, right? So this is take 2, and this is take 3. So in take 2, we use disabling interrupt and enabling interrupts for our critical section. Now we're using Mutex, the SpinLock, for our critical section. And so they're very similar. So we just got rid of the need to disable or enable interrupts by using the SpinLock. Okay. So this is basically putting everything that we have seen all together. So this is the first try that we did using disabling interrupts and enabling interrupts. This one is the second try where we added a value which was either free or busy. Then we talked about SpinLock, and this was our first implementation. And then we amended this by using the SpinLock to get the second implementation. So we've seen so far 4 different types of implementations of mutexes and SpinLocks. The last one being the one that addresses all the issues that we had. The last implementation, basically this one, we can give it to the user because it doesn't use special instructions that are, disabled in the user mode. So we can use it in the user mode. It can be used in a multiprocessor. It does not disable interrupts, so the system can get interrupted, which is good. And the amount of time that you're busy waiting is minimized, right? So we're going to busy wait only for few instructions until we. So if you remember that example that I said, that if you have this mutex.lock and then 2 minutes of critical section, and then mutex unlock. So let's say you have these 2 minutes of critical section. Now, if another thread from another processor calls lock, it's not going to busy wait for 2 minutes. So it's going to just busy wait a little bit if the state of the mutex is being manipulated with someone else. If not, it's going to get suspended, right? So it's going to see that the value is busy, and it's going to just be suspended by the scheduler, and you're going to start running someone else. So you don't need to busy wait for 2 minutes. You can just start running someone else. Okay, now a little bit of how mutexes are in fact implemented inside Linux. So in Linux, they have done some improvements for performance. In particular, they have 2 paths, a fast path and a slow path. So in the fast path, they just check to see if the mutex is locked or unlocked. If it is unlocked, they just used test and set to atomically make the mutex locked. And if it is locked, then they go the slow path, and then they suspend the thread. So it's kind of like this. So they have this counter, which if it is unlocked, the counter is 1, and if it is locked, the counter is less than 1. It could get negative. So, and it's atomic. So they put this atomic so that it gets incremented and decremented atomically. You can't get interrupted in the middle of incrementing it or decrementing it. And then there is this SpinLock mutex, and then the queue. So we just added one more element to what we had before. So in the fast path, we just atomically check this variable, and if this variable is 1, then we just make it 0, basically locking the mutex, and continue. So this is very fast, just with a single atomic operation, which we check and we lock the mutex. If, however, the value is less than 1, let's say if it is 0, then we just call the lock that we saw, the long one, which uses the SpinLock and all of that, right? So to avoid this SpinLock, we just added this step to make things faster. Yeah. So just note that this guy here atomically decrements this counter, right? That's all it does. This is another instruction in x86 that you can atomically increment or decrement and then return the value that was stored initially in that address. Okay, so I'm over a time. Let me see what we have here. Let me do this last slide, and then next lecture we can start talking about semaphores. So few things about this the implementation that we've seen so far. So far I talked to you about how kernel can implement mutexes. Now, if you have a kernel task, your kernel task can just call these lock and unlock as function calls, right? And everything is going to be fine. If you have user code and user mode operations, then it's a little bit different. So you probably want to have some notion of system calls to then call this mutex.lock and mutex.unlock, right? And that could actually be a little bit tricky, and you have to be careful, because when you have system calls, you disable and enable interrupts. So you have to, when you design this for user code, so far we've just talked about how to design it for kernel tasks and threads. If you want to have it for something that could be passed to the users and could be used as system calls, you have to be careful about the disabling and enabling of interrupts. So there has to be some more tweaks to this to work for user threads. Yeah, that's pretty much it. So hopefully from on Tuesday we'll start talking about semaphores. I'm unfortunately a little bit behind. Discard. I was hoping to finish this, but unfortunately I can't. So it's okay. We'll finish this hopefully on Tuesday. So let me see. There are two questions. Since critical section should be avoided when possible, doesn't this mean busy waiting is just the norm when we use mutexes and semaphore? And the answer is yes. Correct observation. So busy waiting is almost impossible. Avoiding busy waiting is almost impossible. So all you can hope for is to minimize the amount of busy waiting that you do. So very good question. Yes. So indeed, you know, kind of busy waiting is unavoidable. All we hope for is to minimize the amount of busy waiting we have. Another question, if an interrupt handler gets suspended, won't this mean higher priority interrupt starts running? The thing is, you cannot actually suspend an interrupt handler, because interrupt handler is not a thread, right? It doesn't have a TCB. An interrupt handler is not a thread. So you have to be careful. Actually, this comes in your exams. Interrupt handler is not a thread. We don't have a TCB for interrupt handler, right? Interrupt handler is a handler. It runs in the context of another thread. So it cannot be suspended. It cannot be scheduled. When an interrupt happens, we handle it right away. We cannot suspend it and then later on schedule an interrupt handler, right? Another question, could you go over the Linux mutex code quickly? I thought that I did, didn't I? Yeah, so this, you attempt to decrement. So for lock, you attempt to decrement. Now, if the result that is returned is, so let's say if it was 1, so you have unlocked, you have locked it. So if it returns 1, then you jump to this 1 and you enter your critical section, right? So this is the path. This is the fast path. So you just locked the mutex very fast with 2 instructions, 1 to decrement and 1 to check the result. However, if the result was less than 1, it means that the mutex was already locked Then you call the slow path. So here you call the lock, the proper lock that we implemented in the previous slide. So you go to the slow path. So you go through the, acquiring the SpinLock and suspending and all of that, right? But so the reason that they have this fast path is because of the observation that usually mutexes are free. Most of the time, mutexes are free. So if they're free most of the time, then lock, we want most of the time when you call lock to be fast, like just it was free, make it unfree and continue. So you don't want to go through all those steps of locking. So that's why you have this fast path. Another question, it would be great if we could have 50-minute lectures. Thank you, you're welcome. Okay, thank you for sticking around, and thank you for those of you who are watching the lectures. Take care, be safe. Talk to you on Tuesday. Bye-bye.